Hello and welcome again. In the last video, we have studied some exercises related to well-ordered principle, first principle of finite induction and second principle of finite induction. We continue with the exercises. In today's lecture, we will study some more exercises about the said topics. So, before going to the exercises, we have to make a remark that we can show that if n is integer, then there is no integer p such that this p between n and n plus 1. Okay. It means between two consecutive integer there does not exist any other integer. We assume that there exists such integer, then p minus n, because p is greater than n, so p minus n will be positive. So p minus n is an integer between 0 and 1, because this p is between two consecutive integer n and n plus 1, so the difference between p and n will be less than 1. So p minus n will be a number which is greater than 0 but less than 1. So it means p minus n is an integer between 0 and 1. But we have already proved in the last lecture that there cannot be any integer between 0 and 1. So contradiction. It means there does not exist any integer between n and n plus 1. Okay. Next question is question 5, and the statement is that prove that for each positive integer n is greater than or equal to 1. That is, 1 is the smallest positive integer. Means we have to prove that 1 is the smallest positive integer. So the condition is that is p1 is true for n is equal to 1 clearly, that is 1 is greater than or equal to 1. So the condition is true for n is equal to 1. And now suppose that pk is true, that is 1 is less than k. That is hypothesis. And now we will prove that 1 is less than k plus 1. Clearly, if 1 is less than k and k is less than or equal to k plus 1, this means 1 is less than or equal to k plus 1. This means pk plus 1 is true. And then by first principle of finite induction, pn is true for all n greater or equal to 1. Okay. Next exercise is question 6, and the statement is that prove that 17 divides 3 multiplied by 5 to raise power 2n plus 1. Okay, one thing which should be clear is that this dot is not the point. It means this number is not 3.5. Actually, in number theory, we deal only with integers. For non-integer, we will not deal with non-integer in the number theory. Whenever there will be written like 3.5, it means actually 3 multiplied by 5, and that will be 15. Or if 3.5 to raise power square means 3 multiplied by 5 square. So here 3 multiplied by 5 to raise power 2n plus 1 plus 2 to raise power 3n plus 1. So in number theory we will not deal with the decimal portion. Okay. Solution. We have to show that 17 divides this number for all n greater than or equal to 1. So we consider that P1, condition for n is equal to 1. Instead of n we put 1, then we will get 2 plus 1 plus 2 to raise power 3 plus 1. Instead of n we put 1. So 3 into 5 cube plus 2 to raise power 4, which is actually equal to 3 into 125 plus 16, and that is equal to 391, and 391 is divisible by 17. Divisible mean whenever we will divide 391 we should get complete integer, and whenever we will divide this we will get 23. So 23 is an integer without any decimal parts, so this means 391 is divisible by 17. Okay, so this is true for n is equal to 1. Now we suppose that condition is true for k. This is actually hypothesis is true, and it means 17 divides 3 into 5 to raise power 2k plus 1 plus 2 to raise power 3k plus 1 is divisible by 17. Okay. Now consider that pk plus 1. We have to show that 17 divides the expression or the number for k plus 1. Okay. We consider 3 into 5 to raise power 2 into k plus 1 plus 1 plus 2 to raise power k 3 into k plus 1 plus 1, and that can be written as 3 into 5 to raise power 2k plus 2 plus 1 if we open this bracket. Okay. Okay. Plus 2 to raise power 3k plus 3 plus 1, and that can be, we can write this as, if we take 3 into 5 to raise power 2k plus 1 into 5 square plus 2 to raise power 3k plus 1 into 2 to raise power 3, and that is equal to, actually if we take this 5 as 25, it will be 25 into 3 5 to raise power 2k plus 1 plus this 2 to raise power 3 is 8 times 2 to raise power 3k plus 1. Okay, we just rearrange. If this 25 can be splitted into two portions, that is 17 and 8. This is 17 times 3 into 5 2k plus 1 plus 8 times 3 into 5 2k plus 1 plus 8 times 2 to raise power 3k plus 1. And this, if we take 8 as a common integer, then we will get 3 into 5 2k plus 1 plus 2 3k plus 1. We can see that, okay, instead of here this is plus, not equal. This term is divisible by 17 by our hypothesis, this one, and this term is multiple of 17, so this is also divisible by 17. So this means 3 into 5, 2 into k plus 1 plus 1 plus 2 to raise power 3 into k plus 1 plus 1 is divisible by 17. So Pn is true for all n greater or equal to 1. Now next question is question number 7. Prove that 6 divides n into n plus 1 into n plus 2 for all n greater than 1. It means whenever we will take the product of 3 consecutive integers, the result will be divisible by 6. So we start the solution. For P1, it means n is equal to 1. We get 1 into 1 plus 1 into 1 plus 2, which is actually equal to 6, is divisible by 6. So this means P1 is true. Means the condition is true for n is equal to 1. We suppose, now consider the second principle of finite induction hypothesis, that P into k minus 1 is true, that is 6 divides, if we instead of n we put k minus 1, we get k minus 1, k, because when we will add 1 in k minus 1 we will get k, and then k plus 1, which is equal to k cube minus k. Now consider, it means this is divisible by 6, k cube minus k. Now suppose or consider pk, that is k into k plus 1 into k plus 2, which can be written as k cube plus 3k square plus 2k, and that can be written as, after a little rearrangement, minus k plus 3k square plus 3k. We have added and subtracted the k from the right side of the equation, and that can be written as k cube minus k, and if we take 3 as a common, we will get k square plus k. Now by hypothesis, 6 divides k cube minus k. This is a notation of number theory I write here. Whenever we will say A divides B, we can write A divides B. It means divides A divides B, and or B is divisible by A. Okay. Now 6 divides k cube minus k by our this hypothesis, and 3 divides 3k into k plus 1. We can take k as a common from this term. Also, because this k square plus k, which can be written k into k plus 1, two consecutive integers are being product, then the product of two consecutive integers must be even. So 2 divides k into k plus 1. So this means 6 not only divides k cube minus k, but also 6 divide the second term, which is 3 into k square plus k. This means 6 actually divides k into k plus 1 into k plus 2. This means pk is true, and hence Pn is true for all n greater or equal to 1. Okay. The next question is question 8, and the statement is prove that 4 does not divide n square plus 2 for all n greater than 1. Okay. If n is even, we divide the proof or solution in two parts by taking that n is even and n is odd. We have made two cases. When n is even, then there must exist an integer k such that n will be 2k, and if we put the value of n here, we get 2k square plus 2, that will be equal to 4k square plus 2. And if we divide this by 4, it gives remainder 2 when divided by 4. So actually in this case, when n is even, the whole expression is not divisible by 4 because it is not giving the remainder 0. And the second case is if n is odd, then n must be of the form 2k plus 1. This means instead of this n square, if we put 2k plus 1 whole square plus 2, and after the evaluation of the square, we get the final expression as 4k square plus 4k plus 3, and that gives remainder 3 when divided by 4. As it is not giving the remainder 0, so it is also not divisible by 4, and this means we can say safely 4 does not divide n square plus 2 for all n greater than 1, either n is even or odd. So that's all about this video. Please subscribe the channel and like the video.